Now, you've seen reflection and refraction in everyday physics for teachers, and you may have even taught the basics of them to junior classes. So we won't say much about these, but I'll just point out a few interesting things about them. Now, the first thing is a reminder that when we talk about reflection or refraction, we need to use the construct called the normal, which is an imaginary line at right angles to the surface that passes through the point where the ray hits. So the angles of incidence, reflection, and refraction are always taken from the ray to the normal. Now, there are two types of reflection. One is the one we normally think of as reflection. It's called specular or regular reflection. A specular reflection is what you get from a smooth mirrored surface. If the incident rays are parallel, then they all obey the law of reflection, that the angle of reflection equals the angle of incidence. So they all bounce off at the same angle, and so the reflected rays are also parallel. In exam questions, all reflection is assumed to be specular. But in real life, we often have not mirror surfaces. Imagine we have rays hitting a rough surface, as you can see at the top right there. Each of the rays comes in and bounces off. The law of reflection still has to be obeyed at every point, but the surface is at lots of different angles to the rays, and so the reflected rays come off in all directions. Now, we might imagine a piece of paper is a smooth surface, but on the scale of the wavelength of light, and even if you looked at it through a microscope, you would see that it's actually rough. So the reflection from paper will be diffuse. We say that the paper is scattering the light. Now, most surfaces in real life scatter light. You can derive the law of reflection from Huygens' principle, which we remember tells you how to go from one wavefront to construct the next. In this case, we've got two rays, 1 and 2, coming in to meet a surface at A and C. Now, the line AB is a wavefront, and to construct the next wavefront, we make the rays move an equal distance in the next interval of time. So the ray from A has moved on to D, and the ray at B has moved on to C, which is another point on the surface. So the new wavefront is now the line joining D and C. We can look at the two triangles, ABC and ACD, and they have the side A to C along the surface in common. And the sides shown by the dotted lines AB and CD are equal in length because the rays are parallel. So that means that the angles gamma and gamma dash are equal, which leads, with a bit more geometry, to the angles theta 1 and theta 1 dash being equal, and they are the angle of incidence and the angle of reflection. Now a quick look at refraction. Electromagnetic waves, like light, are different from any other kind of wave in that they slow down in a more dense medium. Sound, on the other hand, speeds up. It goes about 5 times faster in water than in air. But light is fastest in a vacuum and matter slows it down. The reason for that is that atoms, and in particular the electrons in atoms, absorb the light, jump to an excited level, and then re-radiate the light, and that slows the light down. It isn't just density that decides how much light is slowed down. It is another property of materials that we call refractive index. We find the refractive index of a material by comparing the vacuum speed of light to the speed in the medium. Now, the refractive index of vacuum is 1, of course, and any gas has a refractive index that is very close to 1. The bigger the refractive index in any other material, the more light has been slowed. You'll remember Snell's law that gives you the relationship between the angles of incidence and refraction at a boundary. It tells us that if n2 is bigger, then θ2 will be smaller. In other words, a ray bends towards the normal in a higher refractive index material. One thing to note is the little pink lines at right angles to the ray. These represent the wavefronts. So even though a ray looks extremely thin to us, on the scale of the wavelength of light, even a thin ray is like a wide channel of light. So there are still wavefronts running across the channel. We can also use Huygens construction to get Snell's law. If we return to our picture of two rays reaching a boundary, we have ray 1 and ray 2. We now add on what they do after passing through the boundary. Now you see that ray 1 that reached the boundary at A while ray 2 was still at B has now slowed down, and so it has only gone to the point D while the ray from B has gone as far as C, which is at the boundary. So the new wavefront, which is the line joining C and D, is at an angle to the old wavefront. Now, adding in the amount of slowing using the refractive index, a bit more geometry gets you to Snell's law. Now, you don't need to be able to do this, but you can take your time and look through the steps again if you are interested.